Hello everyone. In this video, we will continue to discuss topics in 9.3 interference. In particular, we will discuss the modulation of the double slit interference pattern by the single slit diffraction effect, as well as discussing multiple slit interference and ultimately diffraction gratings. To revisit the double slit, we've seen before in sort of diagrams and pictures of the double slit effect that when light is shown on a double slit, the final result is not only the double slit fringe pattern, but it is the double slit fringe pattern modulated by the single slit diffraction pattern. So if we take a look here, we can see the double slit fringes in our double slit pattern. They're right here, those closely spaced bright spots. But we can also see sort of this shadow or echo or envelope of the single slit pattern, with primary minima found here and here. And you can see that by direct comparison to the single slit pattern above. If we were to graph these two things, we would find that a pure graph of the double slit pattern expected in our derivation in topic 4 would look like this, with peaks at particular intervals given with spacing S. So the space between the slits, or the distance between the slits, is little d, and the fringe spacing is S, and that's what we would see right here. Notice this graph is given in terms of the angle, where the angle is actually little s, the fringe spacing, divided by big D. Notice that that graph of the double slit interference pattern and this graph here in section B of the single slit interference pattern combine to produce the final interference pattern for the double slit shown here. Whereas you can see pattern A is sort of cut down or modulated by pattern B. And that's exactly what we're talking about. Which means that given a graph, like in C, of an actual double slit experiment, you can determine both the single slit diffraction pattern and find theta. Theta in this particular case would be around 12 degrees, as well as determining little s over big D, which would be given by, although it would be difficult to read, the space between those peaks here and here, for example. With slit spacing and slit width that is closer together, as in this particular graph right here, that is more obvious. So in this graph, the single slit diffraction pattern gives a primary minimum of about 20 degrees, and the double slit fringe spacing angle, so theta equals little s over big D, can be found by looking at the positions of these maxima, which appear to be about 8 degrees apart. So what happens when you increase the number of slits, when you go from 2 slits to 3, 3 to 4, 4 to 5, etc.? Well, there are a number of effects that you need to know about, and we'll discuss. The first thing to do, though, is to take a look at that pattern. Okay, so one slit you can see right here, and then this is our traditional double slit pattern, sort of zoomed in a little bit, but you can see that fringe spacing. And then as you increase the number of slits, there are a number of effects. Okay, there are a number of effects. So to explain them in order, the first thing that happens is that those maxima, okay, the maxima of constructive interference, become narrow. And that is proportional, so the width is proportional to 1 over n, where n is the number of slits. As n increases, that width decreases, so they become narrower and narrower and narrower. And we can see that in our graphs of the single slit, the double slit, triple slit, and a quintuple slit here. You can see that those maxima become narrower and narrower. The reason for that is that as you increase the number of slits, then any angular deviation from that point of perfect constructive interference, you start to get more and more destructive interference. So there's a smaller angular range for the path differences from 5 slits to line up perfectly than there is for the path differences from 2 slits to line up perfectly. And so you end up getting sort of these narrower maxima. But the intensity of the maxima go up. And to think about that, think about the number of points, all right, of light that are arriving at every point of perfectly constructive interference. With a double slit interference pattern, you're having 2 amplitudes worth of light, and therefore 2 squared of the original intensity at that central maximum. Whereas with 3 slits, you have light coming from 3 different points, and so 3 amplitudes worth of perfectly constructive interference. This gives an intensity of 3 squared I naught, or 9 times I naught. This pattern continues, although I can see in my notes I've written 4 squared here. This should be 5 squared times I naught, because there are 5 slits. So the intensity of the primary maxima is n squared times I naught. As a secondary thing to know, they don't often ask about this, but it's not a bad idea to know. You also get some secondary maxima, and you get secondary maxima because sometimes some of the slits line up for constructive interference, but not all of them do. And so, as it turns out, in every case, and this can be proven, although it's outside the scope of this course, you will get n minus 2 secondary maxima. So in the case of 3 slits, you get 3 minus 2 secondary maxima. That is 1 secondary maxima in between these maxima here. And in the case of 5 slits, you get 5 minus 3 secondary maxima. Those are these tiny little bumps in the multiple slit diffraction pattern. So you increase the number of slits, increase and increase and increase, and what you get ultimately is what is known as a diffraction grating. So at about 20 slits, we can approximate this as a diffraction grating, where we assume there are effectively infinite numbers of slits, and we will discuss that in the next video.